Good afternoon to all of the attendees from this new edition of the Fenix webinar. We are today in our 18th edition. And today we also have Petra Ritter with us from the Charité University Medicine of Berlin in Germany. So thank you very much for coming and being today our speaker. And before we start, I wanted to remind all our attendees that are connected online to this webinar that I wanted to remind them that they can address the questions towards the end via the question and answers button or also via the chat function. And just also to remind them that this webinar will be recorded and it will be posted on the Human Brain YouTube channel probably tomorrow. And we'll tweet about this as well and via our Fenix social media networks. So as I said, I want to introduce myself. I'm Renata from the Barcelona Supercomputing Center. And now I'll give the floor to our speaker today, Petra. So thank you for coming today. And I'm sure that you will give us a very interesting speech today.
Thank you so much, Renata, for this great introduction. And welcome everyone to this webinar, how to implement a secure processing pipeline for human data. As you probably know, many fields of research deal with personal data. And for instance, human digital twins are a common basis for health research, but they contain sensitive data. And several studies have shown what kind of information you can retrieve from such kind of complex personal data. For example, here you see a study where it has been shown that from radiologic imaging data of the brain, it is possible to infer behavioral and demographics measures like fluid intelligence or age, but also very private information, how satisfied you are with your own life, for example, or how long you can sustain attention. So this is highly personal information that can be inferred from brain imaging data. It has also been shown that it needs only very few data points in order to re-identify a data subject or the person behind the data. Also, from radiologic images of the head and the brain, it is possible to reconstruct faces and via face recognition software to identify the person behind the data. And even if the routine defacing algorithms are employed on those kind of head or brain scans, and seemingly the faces have been removed, it is still possible because of the very complex kind of encoding of information in this data to reconstruct again the faces and to use this information for re-identification of the data subject or patient. And last example I want to give you, there was actually already a lot of imaging and health data exposed in Europe and also beyond Europe. There are radiologic data management systems that are commonly used by research institutions and by hospitals, and they turned out to be not secure, and a lot of data has already been leaked out. So this is also a source to match actually new information with this already leaked information and to easily re-identify the data subjects. Since it's highly sensitive information, and in particular, if we talk, for example, about complex brain data, the data would contain information about the health state of a subject. This information needs to be protected, because if it is not protected and unauthorized people get access to such data, this can consequently harm the data subject. So for example, it's possible that they cannot get an insurance, they will not be accepted for a job, or also they can experience stigmatization, for example. So therefore, health data and personal data in general need to be protected, and there are different possibilities how to do this. One commonly used is anonymization. This means that all the identifying information has to be removed from the data. So there's no possibility to re-identify the data or the data subject that is connected to the data. For brain research, what would that mean? That would mean that you would have to average, for example, 1,000 brains to be sure that the biometric, the unique identifying information, kind of fingerprint information, has been removed. And with this, the data would be for many types of health-related research useless, because it is exactly this unique identifying fingerprinting information that is important for this kind of personalized health research. So anonymization is often for health research not really an option. Pseudonymization means that the primary identifying information is removed from the data and kept separately behind technical measures that protect from unauthorized access. But typically, there's a notion that the primary identifying information is moved for pseudonymization. That would be the name, the birth date, the address. And the actual biometric information would still be in the data, the fingerprint information, for example, brain activity or the structural information that is unique. And with this, this kind of pseudonymized data would be still personal data. They still would contain health information, and therefore this is sensitive data that needs to get protected. And in different regions of the world, there are different regulations how to protect personal data and in particular also health data. These legislations are differing, but not just the rules, the law is differing, but also the definitions, the terminology is used, for example, for anonymization, pseudonymization, there are differences. And therefore, when speaking about this topic, it's very important to make sure what kind of definitions have been applied. So in Europe, we have the General Data Protection Regulation, GDPR, in place since 2018. And importantly, in Europe, the personal data and health data do not fall under property rights. They cannot be owned. According to GDPR, there can be 3 different roles related to personal data. The role of the data subject, so this is the person from which the data have been acquired. The role of the data controller, this is a person who controls what is done with the data, and the role of the data processor, who can act on behalf of a data controller. And the data controller and also the processor, they are responsible for protecting the rights of the data subject. So typically, a researcher who determines the purpose of processing of personal data is the responsible person. So the researcher would be the controller, and with this, he is responsible to provide the proper protection and to make sure that the rights of the data subjects are not harmed. So for this, the data controller needs to take care of many different organizational processes. And here you see the different roles or stakeholders that are involved in these processes. So first of all, we have the data subject, and the data subject needs to provide consent for the processing of their data. Then we have the already mentioned data controller, that would be in most cases the researcher, the PI, who determines the purpose of processing and who also needs to ensure that all the technical and organizational measures are in place. And one of the organizational measures is that an ethics vote is available. So the purpose of the study and the way how a study is performed needs to be approved by an ethics board if it is related to the processing of personal or health data. Then also there needs to be a risk assessment, and usually if health data are involved, this means there needs to be a data protection impact assessment. The data protection officer needs to be consulted, and they need to provide a vote on the data protection impact assessment. In addition, if the data are being processed on compute infrastructure and cloud infrastructure or on particular hardware, there need to be agreements with the service providers, for example, the cloud providers and the infrastructure hardware providers, that make sure that certain measures are in place that protect the data. And for this, you need service level agreements with these service providers. In addition, of course, you need the technical measures that are in place, and therefore it's important for the researchers to have access to infrastructure that provides the proper technical measures like encryption, access control, sandboxing, and automation of certain processes. So in the past years, we have been involved in several projects that actually focused on the development of such secure, protected environments and workflows for sensitive health data. The most important ones are listed here. This is an EOSC project still running since 2018. Then the two phases of the Human Brain Project, SGA2 and SGA3. SGA2 was the co-design project, the virtual brain, that has developed GDPR-compliant personalized brain simulation workflows on the Fenix infrastructure. And then the follow-up project that is running now in SGA3, the Health Data Cloud, that provides a secure processing environment, a federated environment for health data, also using partially Fenix infrastructure. And here on the right, this is a new project that just started in July this year that scales up the developments of the other projects, EBRAIN-Health. At the beginning, I want to show you the GDPR-compliant workflows that have been developed as part of the co-design project, the Virtual Brain, and SGA2 of the Human Brain Project. And as you probably know, EBRAINS is the research infrastructure of the Human Brain Project that is powered by the Fenix compute centers, the high-performance computing centers that provide the compute and storage for EBRAINS research infrastructure. EBRAINS research infrastructure has more than 5,500 registered users, and it provides a lot of services related to neuroscience that support researchers to do their work. And these are the different service categories. The main focus of the tools that we have integrated with EBRAINS and for which we provide the GDPR compliance services are linked to brain simulation, to personalized brain simulation. And what you see here is are different software components shown in bright blue that have been linked with the core or basis services of EBRAINS that are shown here in the middle column, and that have GDPR compliant technical and organizational measures in place so that personalized data, health data can be processed on this infrastructure. The components include the virtual brains simulation framework, then also processing pipelines for radiologic imaging data of the brain to generate the derivative data that are needed to build digital twins of brains and to run simulations. And then some advanced tools like multi-scale simulation engines that can couple the whole brain simulator to other more detailed simulators, and some code or software that has been optimized for parallel high-performance computing. And there are also interfaces to other software components like the digital atlases and the neurorobotics platform. So the simulators, the personalized brain simulators can draw from these resources as well. But importantly, the software can be run on the infrastructure that is provided by EBRAINS, high performance computing, and the cloud infrastructure OpenShift that is provided by Fenix, and also make use of the knowledge graph for data discovery and data ingestion, and the collaborative workspaces that provide access to data storage, to the Jupyter Lab, and also to Office tools. The services are also integrated with the authentication system of EBRAIN, so there's a single sign-on possibility. The details of these integrated services and also the code repositories can be found in this publication. And the services themselves can be reached via this URL directly via EBRAINS. So the first tool I want to show you is the cloud virtual brain simulator that can be accessed via the website. As you can see here, via the virtual brain entry point, you find several services, and you see the EBRAINS cloud simulator. And, when you have already authenticated with EBRAINS, you can directly access the software in the cloud and start setting up a simulation. You can use the graphical user interface of TVB, which has the same functionality as you would have downloaded the software and installed it on your local computer. And oops, wait a second. So this is a simulation that is running. As I mentioned already, the TVB authentication is integrated with EBRAINS authentication. So when using the virtual brain simulator, you get this message and you grant access privileges to TVB for the information that is already stored with the EBRAINS authentication system. So that will be your full name, your email address, the association to certain units and groups. And this is a very high-level description of the architecture. So you have the TVB web interface, and this interface provides the possibility of encrypting your data. So it provides a service to several users. It has a HPC backend provided by the Fenix supercomputing centers, and also the option for secure data storage. And as mentioned already, there's integration with the authentication tool of EBRAINS via Keycloak. This is now the very complex workflow behind this TVB web simulator. And we can go through it step by step. So the user would authenticate with their EBRAINS login via the HPP or EBRAINS IAM, Identity Access Management. Then they can use the new functionality of TVB to encrypt their data and to upload the data to the CSCS high performance computing facility, to the Scratch of CSCS in this case. We are also having the option to do the same on the Jülich supercomputing center. So presently the users can choose between Jülich and between CSCS for their processing. So the data are being transported in an encrypted form, and the processors, the algorithms that are to be applied to the data are transferred in an unencrypted form. Then a sandbox is being created, which the data are being mounted. And then in this step, the user is authenticated on the TVB web portal, and the key for decrypting the data is retrieved within the sandbox running on CSCS. And with this decryption key, the data are being decrypted. Then the processing, so for example, the brain simulation is executed. The state of the simulation is also queried by TVB Web and monitored. And then at the end of the processing, the data are getting encrypted again, and the sandbox is being terminated. The encrypted data then are again in Scratch and are downloaded by the TVB Web, and can be accessed by the data controller, the user. So with this workflow that includes encryption and sandboxing, it is indeed possible to securely process personal brain data on a Fenix supercomputer that does not provide data protection by default and by design. Here I show you another workflow. So we have seen the TVB web simulator. We have also pipelines for processing radiologic imaging data in place. They are provided as Docker containers, and they provide several steps of processing of functional and structural imaging data to provide then at the end the kind of data that are needed to build the personalized brain models. And this is a multi-stage or state process that involves different infrastructures, the user computer, the cloud system provided by EBRAINS, and the high-performance computing backend. And typically in these workflows, the Jupyter notebooks provided by the collaboratory serve as the front end to control the processes and submit the processes via Unicore to the high-performance computing backend. Also, as part of the Docker containers, we have an orchestrator function that performs the decryption and encryption and the sandboxing, and that also includes data-led in order to provide provenance tracking. So each new data derivative is stored on a new version, and the associated processes that have been applied are tracked and can be recovered. So each processing activity becomes reproducible. And yeah, as mentioned before, for the TVB Cloud simulator, we have a sandboxing mechanism, and only during the sandboxing, the decryption of the data happens, and the processing takes place, and the data are then encrypted again before the sandbox is destroyed, and the data are sent back to the user and legitimate data controller. This is the same workflow in a little bit more detail. We have the data controller, we have the EBRAINS Cloud, and we have the high-performance computing backend. And we use here public cryptography. So the data controller authenticates with EBRAINS. They generate a public key, and at the same time, the HPC generates a public key. So the user has a private key, the HPC instance has a private key. And with the public key of the HPC instance, the data are being encrypted. In this encrypted form, they can be sent via the cloud to the HPC backend, where again, we have the sandbox started now for the image processing pipelines, but very similar to what we have seen previously for the simulator. And within the sandbox, the processing takes place, and the data are being then, the results are being encrypted again with the public key of the user, and only the user has a private key to decrypt the data. This setup, in principle, also the administrator of the infrastructure in the default state would not be able to access the data, and actually is also not authorized to access the data. The processing workflows contain also the possibility to directly generate metadata. that can be then used to ingest the generated data derivatives in the graph database of EBRAINS to make the results, the derivatives also discoverable. What you see here is such a file structure of metadata that are being generated that contain some basic information about the specimen, animal, human data, the data authors, the license, and the individual data subjects. So each data subject then has again another file here that contains more detailed metadata for the specific data subject. And in EBRAINS, we have the knowledge graph that provides the functionality to store this kind of information and to make it searchable. We use mostly the OpenMinds schemas, metadata schemas, to annotate the data that provide the ontology, the vocabulary, and that use the JSON-LD syntax to provide the linking, the structure of the different metadata pieces of information. As mentioned, the metadata then are ingested via the knowledge graph technology in the graph database. And with this, the content of the OpenMinds schemas that are provided with the data can be searched via a visual graph explorer or via programmatic interfaces. Then I've mentioned that we also have optimized code for personalized brain simulation on high-performance computers that uses the possibility of parallel processes. And this is C code that has been optimized. And that is this C code very popular, and several publications already have used this code on EBRAINS. Including publications by authors outside Charité. So Charité has developed this code, and here you see, for example, a publication, subject-specific features of excitation inhibition profiles in neurodegenerative diseases, where the same code has been used by other authors, which shows that it is really usable, which is actually nice, because this is the purpose of these services, that they can be used by other researchers independently. Also, there's a possibility for personalized multi-scale co-simulation. This is also directly accessible via the EBRAINS website and portal. So you will find there a button where you can access this. And here I show you a recent use case that has been the multi-scale co-simulation of the virtual brain with another simulation framework, Nest and Anarchy, so two microscopically detailed simulators have been coupled to the virtual brain macroscopic simulator to simulate a Parkinson's brain with a very detailed network of the basal ganglia and the thalamus to optimize the site and the pattern of stimulation in Parkinson's disease. So multi-scale co-simulation allows that some regions of the brain are simulated at a coarse degree of resolution, while other regions of the brain are simulated at the level of spiking networks of individual neuron cells. And again, this is personalized data, so you need to have this protected environment. But what is also possible is to use the interface to the digital atlases and EBRAINS to draw additional information and inform the brain models. So here, for example, we see the receptor densities in different brain regions that can help to increase the biological plausibility of our model by heterogeneous parameterization. So the parameter values chosen would depend on the distribution of the receptors in the brain. And these receptor densities and also genetic expression information and other information can be obtained via the new Zebra Python client that has been developed in EBRAINS by the Jülich Forschungszentrum. And then there's also the possibility to couple the brain simulator to the neurorobotics platform. And with this, the activity that is being simulated can be directly linked to simulated effectors or organs, or for example, the hands, that then show directly the consequences, the behavioral consequences of the activity, simulated activity in the brain. And we can systematically explore how, for example, changes in synchrony and synchronization in an individual brain, as we can find it actually also in real persons' brains, leads to different performances, which provides the possibility to mechanistically understand inter-individual behavioral and performance differences. So as you might have noted, this is all very personal information, and the research in focus is personalized brain research. And again, therefore, we need the GDPR compliant setting in place. And this also includes for each individual study that a data protection impact assessment is performed. And for the tool that we are providing here in the Fenix infrastructure, this has been done. There's a document of several pages that analyzes possibilities for attacks and for unauthorized access of those data, also manipulation of the data or loss of the data. And this data protection impact assessment that needs to be done. This is part of the GDPR law. So if we are doing research on health data, data protection impact assessment needs to be done if such compute infrastructures are being used. And this is also connected to a security concept that has to be generated, that also exists for these workflows, that describes the organizational and technical measures that are in place to protect the data. It also requires a concept for operation that describes how these services are being operated. For example, they also elaborate the regular maintenance that takes place, incident responses, data recovery, data backups, and user management. We also have a roles concept. This is also required. And as you can see here, there's a role of administrators, data controllers, and processors, and they have different degrees of permissions. And of course, then each user also has to agree to the EBRAINS general use terms and the EBRAINS data use agreement. But on top of this EBRAINS data use agreement, because we are dealing with personal data, and the service provider Fenix or EBRAINS act as processor on behalf of the user, there needs to be also a processing agreement in place. And for this, we have actually a so-called standard contractual clause that is provided by the European Commission that is being used. So each user concludes a standard contractual clause with the processor, the service provider. And with this, the processor is authorized to perform the processing on behalf of the data controller, the user. The security concept includes information about possible attack scenarios and protection measures, authenticated end-to-end encryption, access control and authentication, firewall and sandboxes, logging, monitoring, incident detection and handling, user control, secure deletion and data ephemerality, regular updates, human resources, and shared responsibility and compliance. Importantly, in such a setting, the liabilities are distributed. So it's not the user or the infrastructure or service provider who carries the entire liability for protecting the personal or health data, but this is distributed, and therefore it needs the contractual service agreements between the different parties or stakeholders to ensure the liability for certain technical and organizational measures to protect the data. So here we have the infrastructure provider, the cloud service or service provider EBRAINS, the software service provider, and the user. And we see here the protective measures and roughly who is responsible for each of those. Of course, this is much more detailed. There's a much more detailed concept. It's just a rough overview to give you an idea. And this is also just to give you an idea, the set of necessary agreements that need to be in place that have been elaborated between EBRAINS as a service provider and the infrastructure provider. So here this is, for example, CCS as one of the Fenix infrastructures, and the Charité as one of the service or software providers. So between EBRAINS and CCS, there are all these agreements. Between Charité and EBRAINS, we have all these agreements. And then, of course, EBRAINS as a service provider also concludes the already mentioned agreements with the user, including the standard contractual clause that authorizes EBRAINS to act as a processor on behalf of the user. So in summary, for these TVB EBRAINS integrated GDPR compliant services, the TVB EBRAINS workflows incorporate privacy by design and by default. Workflows are hosted in the infrastructure of EBRAINS. Protection is governed by strict technical and organizational measures. Appropriate policies and procedures have been developed. Clear definition of roles, rights, and responsibilities. Transparent use and access policies that promote fair and democratic access to the workflows. Usage is formalized through concrete agreements. Users need to prepare a data protection impact assessment reviewed by the relevant data protection authorities before using workflows if they process personal information. And user accounts restrict data access to authorized persons. This was the project Virtual Brain, co-design project, the Virtual Brain, that has been developed under SGA2 and the Human Brain Project. And what I just showed were the outcomes, the results that have been made available to the users of EBRAINS. I want shortly, at the end of my presentation, also introduce some other developments, partially still under development, partially already realized. So the follow-up project of the Virtual Brain project in SGA2 is the Health Data Cloud that provides data protection and data protection by design and by default in a federated system. So we have secure processing environments at different nodes. It's a peer-to-peer network where we have equally privileged nodes, for example, at the Charité, at the EBRAINS infrastructure, at other partner infrastructures, for example, Oslo University Hospital is also involved. And these infrastructures are interoperable. And there's actually one central infrastructure that provides the services of this network to the global user community in EBRAINS, and therefore it has additional services like the knowledge graph that provide discoverability of the data in the central node, but also on the connected satellite nodes to the user community. The interoperability between these systems enables exchange of metadata and also of code. So containerized workflows can be transferred from the central hub to the decentralized nodes, for example, at the Charité or the Oslo University Hospital or other nodes that are becoming part of this network. And the processing of the data can occur decentrally without moving the data necessarily to a central node. Nevertheless, the existence of the data can be discovered via the central node, via the knowledge graph, because the metadata are being ingested from the decentral nodes centrally. So what is now the solution that provides the security in the different nodes? I mentioned the secure processing environment, and here you see the label VRE. This is a virtual research environment. This was an environment that has been developed at the Charité under the EOSC project, which I will show you in a moment. But before I go there, I just want to explain you the user journey of this health data cloud construct that is presently under development in EBRAINS and SGA3. So the user journey will be as follows. First of all, a user needs to be able to discover health data in the infrastructure, in the EBRAINS infrastructure. And for this, it requires a metadata publication service and a data search service. And this is what we have seen earlier is provided by the knowledge graph. So the knowledge graph makes the metadata public and also provides a search interface to discover certain metadata, and this is the connected data in the graph database. Then the next step is data permit application, and because we are here focusing on health data, this is a little bit more complex. So an interested user needs to be able to submit a permission request to access, for example, health data. And then there's a review pipeline by the data controllers who are authorized to grant this permission. And this involves several steps at which we want to look later in order to lawfully grant access to such sensitive data. Then comes the next step, the data usage step that includes data integration services, data provision services, and data analysis services. So for example, data can be moved if necessary from a data center to another data center that provides, for example, the necessary high performance computing power, and also here all the software tools that are being made available, the simulators, the processing pipelines, the atlases that can be used to process and analyze this data. And then comes the project finalization phase, where the results are prepared for publication again. So the data, the derivatives that have been generated, the results that have been generated are annotated with metadata and ingested again in the knowledge graph. And this is the loop closes, and the data become discoverable and are subject to the metadata publication service and the data search service. So now, how can such a setting be provided for sensitive health data? This was subject to the EOSC project developments, Virtual Brain Cloud, 2018 to 2020. We had an extension now until 2023, so the end in a couple of months. And the main output was, or one of the main outputs, a secure processing environment, virtual research environment that has been deployed on premise at the Charité data center. Charité is a big university hospital. The IT data center is a critical certified infrastructure that already provides security certification and several technical and organizational measures to protect the data and the infrastructure. So in a nutshell, we have a front end and a back end, and we also have interfaces to certain data sources and to the local high performance computing, which is part of the critical infrastructure at the Charité. And we have a special room, which is called the green room, where even data with primary identifying information can land. So the data that is highly sensitive, that still contains names, addresses, and birth dates. And in this area, these primary identifying pieces of information can be removed, also using automated workflows and pipelines. So for example, for replacing names or also for defacing brain imaging data. The data can then, by the authorized data controllers, moved in the core zone. So the data still are sensitive, but they do not contain this primary identifying information. And there they can be made accessible to the team members of a project, who would be also authorized people, for example, joint controllers or processors on behalf. These could be, for example, PhD students, postdocs, collaborators, who have the lawful basis for accessing a certain data set that would be granted by the primary data controller access to the data in this environment. And this environment provides several options to process the data. For example, via workbenches, and we have a look at these in a moment. This is just the landing page of the virtual research environment. And here you see different functionalities of the workbenches. So it provides tools for interactive data processing. For example, we have Apache Guacamole for remote desktop and command line interface access. We have also Jupyter Hub to run, for example, Python code interactively, and also the possibility to bring in container workflows. Also, as one of the functionalities, we have Apache Superset to visualize the data that are available in the project-specific data warehouse via dashboards. And each of these workbenches, which are project-specific, runs on a private virtual machine and provides this additional layer of separation to other projects so that unauthorized access is prevented. And there's also from these virtual machines an interface to the HPC backend for utilization of high-performance computing. This is just how it looks inside the virtual research environment. There are many tools for managing data, for version control, for example, then interactively providing data set information. So this was an interactive curation step where the user who brings in data is asked for some basic information about the data set, like the name of the data set, the authors, the license, and so forth. And also there are some validation algorithms included to check for proper data structure and for compliance with specified data standards. Another feature is data lineage. So it's possible for each data set to provide and to browse via going over these little icons, information on the current file, on the upstream and downstream versions of these files, the processing that has been applied to the specific file, and also the transfer of this file between different network zones, for example. And of course, also here, and this is a secure virtual research environment, we have several technical and organizational measures in place, and some of them are listed here. As mentioned already, in this case, the data center already is a critical certified infrastructure that provides a lot of measures for data security and data protection. The virtual secure research environment has isolation of data and resources that is achieved via many different layers. There's encryption, authentication, authorization mechanisms, and very fine-grained access control that is role-based and mapped to the role concept of the general data protection regulations. These are the technical measures. There are also organizational measures. So, for example, here we see the multi-step procedure that establishes the lawfulness of processing. This includes the evaluation of the availability of the subject consent, the evaluation of whether the purpose of processing is compliant with the consented purpose of processing, the evaluation whether it's special category of data according to GDPR, that would be, for example, health data, a risk evaluation, and the evaluation whether it's necessary to do a data protection impact assessment. And only if each of those steps has been successfully passed, then the access to a project with personal data is granted. But with this, I come really to the end. I want to just also inform you that there is a training session. This is by EBRAINS called Simulate with EBRAINS. Can be found on the HBP and at the EBRAINS website. It will take place, actually it starts on the 7th of November and takes place for a couple of days. And then we will also in detail and also with hands-on session talk about these TVB EBRAINS workflows and the Health Data Cloud. There will be very short and quick introductions by myself on the 8th of November for TVB EBRAINS services and Health Data Cloud, each lasting only 5 minutes. And then on the 9th of November, we have a full day. Half of it is used for showing in detail with the code and hands-on sessions the TVB EBRAINS services. And then the second half of the day is used to showcase the Health Data Cloud. And with this, I end my presentation. I thank you very much for your attendance, and I would be very happy to take questions.
Thank you, Petra, for this very interesting presentation and webinar. So I can see one question already in the question and answers. Are the data protection documents also available to the public, including SOPs and TOMs? Thank you.
So not all data protection documents. So if the data protection impact assessment and the external auditing really requires a lot of detailed information, and is done in tight interaction with the actual service and infrastructure providers. But the most relevant security concept information, so the technical and organizational measures that are in place for protecting the data need to be shared with the data controllers, because the data controllers are responsible for protecting the privacy of the data, and therefore they need to ensure that the proper protection measures are in place, and therefore they are to be shared. But of course, this is only true until a certain degree of granularity, and there's a lot of information below this level of granularity that must not be exposed.
Okay, thanks for answering this one. I wanted to say that I've included as well in the chat function the events that our speaker was mentioning today, with a link in case any of the attendees are interested in attending and registering as well. So that you have a little bit more information about the event of that will be held on the 7th of November about the EBRAINS initiative.
Thank you so much, Renata.
No, don't worry.
There will be a lot of opportunity to ask questions, and there will be also the developers of these tools present. So if you're interested in the technical details, I only can encourage you to join us there, and you will directly go into the details of the code.
Okay, so I cannot see any other questions. Bit of information that I wanted to share as well with our attendees today. Okay, just to finish this webinar, I wanted to highlight also as well that there is a call already open, and the deadline is on the 7th of November. That is the Praise ICI call, is the last opportunity for all our potential users to use the Fenix services. So the call is open, as I said before, until the 7th of November. I really want to encourage everyone to use it, and how you can do it via the Fenix website on the link that I've included at the bottom of the slide. Okay, and just to finish, I've also distributed the evaluation questionnaire. It is really important to know your opinion about our organized webinar today, and also to suggest any other future topics, so that we can address all the requirements of all the attendees for future webinars. So please take just the 2, 3, 5 minutes from your time and fill in this webinar, and it's really, really important for us. So I really appreciate your time here. And just to finish, I wanted to encourage you to stay tuned with us via our social media channels that you can see at the bottom of the slide. And also we have a mechanism that you can sign up for our Fenix user forum on the link that I've included in this slide. This is free. You can join for free. And it is important that you can always address any other questions that you might raise to all our speakers or to any of our services that we are offering. And with this, I just wanted to thank you, Petra, for coming today and for your interesting talk. And also I would like to thank all attendees for their time. And I hope I will have you in our future webinars